Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass. Move along, move along. Come inside, the show's about to start. Guaranteed to blow your head apart. Rest assured, you'll get your money's worth.
Alrighty, hello and welcome to the third in our three-part series, MetalForming Live. This summer, this event today is on press brake process and tooling best practices. I'm Brad Kubin. I'm the editorial director of MetalForming magazine here at the Precision Metal Forming Association. And I'm pleased to be joined today by our senior editors, Lou Kren, as well as Kate Bachman. And Kate's going to serve as our moderator for today's session. I want to remind everybody, as we always do, that these sessions are intended to be interactive with our audience. We really want you all to take this opportunity to ask your questions of our esteemed panelists today. They're here to help you out with any press brake issues that you might be having in your shop. So use that question panel on your Zoom screen and please make this as interactive as you can. I also want to thank our sponsors at this time, SEYI, Stamtech, Bystronic, Nidec Press and Automation, Prima Power, and Principal Financial. Without the support of our sponsors, we're not able to bring you events like this one. So with that in mind, please enjoy this brief ad from one of our sponsors, Stamtech, and then we'll be right back here.
Hi, Lee Ellard with Stamtech. We're happy to be sponsoring the third event in the PMA MetalForming Live series. I know this week is primarily about fabrication and fabricating equipment such as press brakes, lasers, and that sort of thing. But hopefully some of you may have some stamping in your operations as well. Stamtech makes stamping presses, and we'd love to help you out with that requirement if it ever comes up. So, and you might actually already be doing some stamping in your plant, perhaps in a press brake with unipunch tooling or something like that. The press right behind me here is a good alternative to a press brake style of stamping application. Still a C-frame press, much like a press brake, but with a bigger bed and more robust giving system and that sort of thing. We also have a lot of other stamping presses. If you ever decide you're going to get into stamping, we'd be happy to help you out. Look forward to hearing from you. Thanks for attending again.
Hi, I'm Kate Bachman, MetalForming magazine's senior editor. Welcome, and thanks for joining us. For all of you who have encountered press brake bending challenges and are seeking help, I'm delighted that three outstanding press brake experts are with us today. Paul Latang, to my right, Justin Talianic, next to him, and Hector Velasquez. Hector is a sales engineer for Wilson Tool Engineer and International. Justin is lead press brake operator at Keystone Fabricating. And Paul, veteran Paul Latang, also known as Dr. Bender, will lead off. But before we get to their sessions, I would also like to thank and acknowledge our sponsors today, whose generous support allows us to bring this to you for no cost.
What SEYI can offer you from a sales perspective is a couple of things. One of them is get to know you. Who are you? What are your business needs? What are the upcoming challenges that you may face? And how SEYI can provide you with a full turnkey project.
It's a very large company, but with a small company feel to it. We have a lot of flexibility and capabilities for both our domestic side here at SEYI America, as well as the support from our corporate overseas. We can really offer our customers a great value for our products, to help them optimize their production, their ROI on the equipment they purchase.
What I feel that makes SEYI unique is the fact that we basically try to help the customer, we help think for them and try to benefit what their needs are or anticipate what they need so that we can better serve them.
SEYI has a very good product. We have a full complement of presses from 28 ton all the way up to 2,500 ton presses, and we have a full complement of parts in-house in Tennessee, and also have service technicians readily available to service all of our equipment.
And typically, whenever we receive a call for parts, we can get them out same day. We have probably 95% of the parts here in Tennessee and Mexico.
SEYI has a very strong service department, very strong service team. We're able to resolve the issue for the customer so that they can continue making parts and continue on with their production.
From the point of finding a press project all the way after installation of the press project, we have excellent people at the factory, we have excellent people in the US, we have excellent people in Mexico that will help you become a satisfied customer.
Hello again. Paul Latang draws from his deep experience as a technical advisor for Pastrana, Galvadi, and other companies, and currently is an independent consultant. Paul will discuss deformed metal parts, the result of errors made, and then step back to where the bending operator or designer took a wrong turn, and then step back even further to the correct actions that would have made and resulted in good parts. Please welcome Paul Latang.
Here today, we're going to outline some challenges fabricators have to take into consideration when assessing recipes for successful bending solutions. The first and most important is the V opening. Too wide of a V opening causes excessive spring back. More importantly, causes excessive spring back variations. A too narrow V crowds the die and exaggerates the typical metal thickness variations. The additional force needed also can overload the tooling. The minimum V opening of 5 times metal thickness and the maximum V opening of 12 times metal thickness must be respected for good bending results. The ideal V opening, or the sweet spot, is about 8 times the metal thickness, or for 1/4 inch plate, about a 2-inch V die. Excessive force concentration can compromise the bending performance by the upper punch partially penetrating the material. In extreme cases, the machine or the tooling can be damaged. Examples of some damaged tooling. Tooling tends to fail in the weakest spot, which is generally at the bottom of the V. And here you can see a die has been split by overloading. Flange length. If the flange length is too short, the part can slip off the die shoulder and possibly damage the bend part beyond repair. Also, more importantly, the part can be ejected into the machine operator. Although the minimum flange is about half the V opening, a safety margin is needed to guarantee the part does not slip into the V during forming. Typically, the minimum flange for 90 degrees is about equal to the V opening times 0.77. Holes near the bend line. This is a very common problem today. Any cutouts inside the V opening are likely to deform are so-called blowout during forming. In this example, you can see to the right that the circles or the round holes are outside of the V die and are clearly formed. The ovals, part of the oval is inside of the V die and is blowing out during the forming. Upper tool interference. Part and upper punch geometry must not overlap. Consideration for bend radius and spring back must be included. On the right here, if the interference, if the part is touching the punch, the bend part will not be parallel after forming. Be aware that similar deformations can be caused by bending too fast. Lower tool interference. The part in the lower die geometry must also not overlap. Here in the example, you can see the die shoulder penetrating the piece part, causing the Z-shape flanges to be non-parallel. Be aware that similar deformations can be caused by gauging errors. When the offset or the Z-shape is less than a ½ inch, an old school solution of a unique hard tool is likely required. Giant radius. Radius deformation can occur when the punch radius is greater than 8 times the metal thickness. Leverage between the punch radius and the die shoulder causes the material ahead of the tip of the punch to deform. Four-sided boxes. When forming four-sided boxes, the punch height must be much taller than the box depth. Punch height must be included in the box depth with the final bend at 90 degrees. Some additional height to clear the ram must also be included. The formula for punch height is equal to the box depth times 1.3 plus an amount for the ram interference is shown in the red on the upper right. Enclosures. Horn tools are used to reach into the corners of boxes that have return flanges. Here's an example of a typical horn tool configuration. Die marks. Die marks, or sometimes called witness marks, are caused by the material sliding across the lower tool shoulders while forming. The length of L1 before bending is shorter than the length of L2 after bending. This difference is causing a drag zone on the piece part. Bend order can also impact part quality. In the example, Rotating the part on the second bend changes the location of where the blank size errors reside in the part. Process A, the blank size variations will arrive in the cross section or the bottom of the piece part. Process B, we change the location of the gauging and the bending to where now the blank size variations will end up in the up leg on the piece part. Thank you.
Wow, that's really fantastic. Thank you so much, Paul.
You're welcome.
You've learned a little bit over the last few years, haven't you?
Maybe one or two things.
One or two. Really, really amazing. So excellent, excellent best practices and warnings about mistakes and so forth. It looks as though we have a couple of questions from the audience. Brad?
Yeah, we do have a couple questions, and you know, if you have questions specifically for Paul, go ahead and pop those into your question panel. Otherwise, you'll be able to ask questions of Paul throughout the session. So the first question, I think, is one you're probably pretty familiar with, Paul, about K-factor. Can you explain the K-factor and why it's important in bending?
Yeah, the K-factor normally refers to the neutral axis. And I think Justin's going to talk a little bit about that in his presentation. But when you're bending a piece of metal, the inside of the bend radius is compressed and the outside is stretched. Between the compression and the stretching, the material is not affected. We call that the neutral axis or the K-factor. If you know exactly where that neutral axis is, you can easily calculate your blank size. Problem is, we can't really assess very well where that neutral axis is going to be, so we have to assess it or take a lucky guess to where it is going to be.
Hector, I see you nodding your head as Paul is talking.
Yes.
Sounds like this is familiar to you too?
It is. I think the most common factor is going to be 0.447, 0.441. So you take the material thickness divided by that, and you're going to be pretty close. But yes, I guess most of the time it's going to be where it's going to be a trial and error type thing.
And Justin, is this something you have dealt with as press
Yeah,
brake lead
and
press
then,
brake operator?
it really depends exactly on what material you're bending, how big the die is, what's the punch radius, all these things will affect it. And so to just blanket say, well, it's just 0.445 or whatever, it's a lot more complicated than that. Each material tends to have its own. I know that for steel, I tend to use 0.445 or something like that. For stainless, I tend to use 0.4. But again, it's all really based on the tooling geometry as well.
Interesting.
If I can add one more.
Please.
If you Google search K-factors and bend allowance and so forth, you may find a number of formulas to assess the K-factor. None of those formulas take into consideration the tensile strength of the material. So everybody knows that lead is going to have a different K-factor or neutral axis than titanium. But the common knowledge is they form the same.
Interesting, really interesting. And Brad, I think I saw one other question.
Yeah, this would be for Paul or the rest of the panel. There's a lot of press, including in MetalForming magazine lately, about servo electric press brakes. They seem to be becoming almost a de facto choice for a lot of fabricators today. Can any of the panelists speak to the advantages or disadvantages of that servo electric style of press brake?
Sure. The servo electric kind of insinuates a direct drive, like a screwdriver or a belt drive. The advantages with the servo electric press brake is you can get an extremely fast acceleration factor and an extremely fast deacceleration factor. So this quick accel and quick decels tend to improve your production rate without impacting the bending speed itself. Of course, you could run the machine faster to bend faster, but then it makes it a little more dangerous. So addressing the accel and the deaccel are important factors for electric presses.
Very cool. And Justin's nodding his head.
Yeah, I think
Have
they
you had any
also,
experience with that?
I think they're also supposed to save a little bit on the electricity because I believe that they only power on the downstroke. Normally they're spring loaded, so they return on their own, which is also a safety feature. In case the press loses power, it's not gonna come down on you, it's gonna go up.
Very cool. That, you know, obviously the price of electricity is not ever going down. So that seems to be something that manufacturers are more concerned about, for sure. So, and going back to your presentation, Paul, you covered a lot of really excellent information. Of all the kind of errors that you've seen operators make and designers make, what would you say is kind of the most prominent, the one that you encountered or had to deal with the most?
Yeah, what I've seen a trend in the industry is everybody today understands some sort of a CAD system, some sort of a way to design parts in an automated fashion. Those CAD systems have no rules built in them for bending. So consequently, you can put a hole or a cutout anywhere in the piece part, and the CAD system, you know, does the simulation and is fine with it. When you take that CAD drawing and you go to the machine and you start to manufacture, you find now that some of the geometry that you put on the piece part now arrives in the bend line and blows out.
So you've experienced that a lot, it sounds like.
Blowout is probably the most common problem you would
Okay.
see on a press brake part.
All right. So just because you can draw it in CAD doesn't mean you can manufacture
And
it?
There is no rules in the CAD system for sheet metal design.
Right. So, Justin, when you were a brand new green press brake operator years and years and years ago, did you encounter something like that where you received a design and the design didn't quite, you know, make it to the manufacturing stage?
Yeah, I've definitely had a couple of those issues, parts that were very close, tight toleranced, and they needed to be very good, and actually we had to put a Z bend on it, a little joggle. And there was a cutout because that joggle had to fit up against something, and it was not designed correctly for the tools that we had. And they were not coming out very good, and somebody else had wrecked and scrapped a bunch of the pieces trying to make a good part because they put it in, they hit it, they just assumed, oh, it didn't work, it was off by 10 thousandths. They moved it 10 thousandths and hit it again, and here that 10 thousandths was a little bit too much because now the blowout had pushed the part in a different direction. So now instead of being maybe 10 small, you were 10 big. So you kind of had to cheat it. You had to use a little bit of knowledge to understand that you can't just put in what in the computer what it says you need.
Interesting. And the remark you made about having to have the right tool for that particular process or material, I'm thinking you know a little bit about that, Hector?
yes, I do. So one of the things that I recommend engineers and the operators is for them to meet. Because to Paul's point, not because the computer allows you to draw it, means that you're gonna be able to form it. So based on the tooling capabilities and the knowledge that you have on the floor, having the engineering and that come together, it's where shops needs to start to ensure that they are making good parts and avoid the costly downtime and the scrap that metal today is very expensive. So it'll cut down on those two things.
Very interesting. And Justin, it sounds like you know, really kind of know your way around the right tool for the right material and the right particular design. If you could tell your designers one thing, what would you tell them?
Stop putting holes by the bend. Yeah, it's really hard because a lot of times the people that are being taught how to draw this stuff, they're being taught how to draw, not necessarily for the best practices for the drawing. And they may put a location of a feature right by the bend line just because they don't really know any better. And the software is not going to stop them because the software says you can do this. But really, if they took a little bit of time to talk to the manufacturer before they just release the print, the manufacturer has an opportunity to say, hey, can you move this? Is it possible? And the earlier you do that in the process, better. If you wait until it's already on the shop floor, it's too late.
So what is not too close to the bend line? Is there a rule of thumb, Paul? A certain calculation and
Yeah, your flange length or your hole has to be outside of the V opening. So sometimes you can manipulate by using a little bit of the smaller V opening. There are some dies, and I think Hector may talk about dies that you can encroach a little bit on the V opening with the geometry. There's not a good solid formula. Just to stay outside of the V depends on the V.
very interesting. So, and in your presentation again, Paul, I just kind of going back to that, there were so many excellent examples of mistakes and problems. And who knew that there could be so many ways to destroy a part, right? Are there circumstances when somebody can, sort of cheat the rules? Sometime when they just really have to put a feature near the bend, or they have to, design something in a certain way that seems like the bend would be out of sequence. Are there sort of workarounds that you're aware of that they can do?
Yes, a multitude of workarounds, and operators do this every day. Unlimited resources, you would buy many different tools that have different capabilities, buy many different machines. There's a lot of different ways you can work around the process by buying equipment. Often, I think as Justin mentioned, is the part is already on the shop floor by the time people realize that there's a problem. So not only now you have to buy a tool, you have to buy new parts because these parts were maybe already cut. So the operator now is faced with salvaging the part. And there's number of different ways. I think we're going to discuss some of those ways coming, but all those ways cost time and money. Right? So now you're pouring huge resources into saving a defective part.
Interesting.
Yeah, many shops now have zero scrap policies. They're not allowed to scrap parts. You have to make it work. Right? Your job, make it work.
Wow, that sounds like a tough order. Well, on that note, we will move to our next presenter, Justin Talianek. By the end of this, session, I will finally pronounce his last name correctly. Justin is a lead press brake operator for Keystone Fabricating, and many thanks to Keystone Fabricating for lending us Justin, by the way. Justin applies his practitioner's experience to sharing creative approaches to press brake challenges. He'll let you in on some tips and tricks he has learned along the way over the past decade as a press brake operator. So I'm very pleased and proud to turn it over to Justin Talianek.
Thank you. So in the past 16 or so years that I've been a press brake operator, I've worked at multiple jobs, and I've worked with a lot of different, very skilled press brake technicians. One of them was a mentor I had. His name was Dan Zoski, and Dan was a very, I'd say, I don't know if you'd say nitpicky, but very focused individual who, me and him had a lot of conversations about perfection. A lot about how even with atoms, if there was perfection, the atoms wouldn't move, we wouldn't have life. A lot of the perfection on a press brake is important. You want to eliminate as many variables as you can. You want to account for as many variables as you can. And the more variables you account for, the better your parts are likely going to come out. Now you're going to have more variables with deformation. How close are the features to the bend line? What shape are those features? What material? Because materials will deform at different rates. All of these are important questions to discuss. Any feature that's residing too close to the die space will fall into the die. If it falls into the die space, the material is going to essentially flow toward the area of least resistance. Anything that is essentially perpendicular to the bend line won't blow out much, but anything that is parallel or at a miter will. And the amount of deformation is going to be dependent on how large your bottoms are. The first solution, if you have a hole, you can reduce the hole size itself in the blank. Now this needs to be done before the part gets cut. But if you reduce the hole size, you're going to reduce the interference in the blank and the die space. And if you do have some small amount of deformation, when you drill it out to the correct size, you're going to remove most of that deformation. Another excellent way is to use bend line slitting. This is essentially just a relief cut that is going to create a weak point in the material. This will keep the feature from deforming because the weak point is right on the bend line. Sometimes you can also use this if your tooling is too short, you don't have enough tooling, you can put some slits in order to reduce the amount of bends you actually need to make. And you will also lower the tonnage. So if you have an issue where you have too much, you need too much tonnage to form the part, your machine doesn't have that, you can put these slits in. Another option is to go to a smaller V opening. These smaller V openings will also reduce the interference in the die space, but likely they're not going to completely eliminate it. You can probably step down a size or two, going down to about 5 times, about as small as I'd like to go. You can also, if the die is too small for your material, you can bring it up a couple degrees and then go into a larger die. And since you already have a little bit of a bend on there, it'll kind of pull around a little bit, but you do have to worry because they will deflect. The blowout there will push your tooling around. So you need to make sure your tools are tight in your machine and that you're holding your part correctly. You're also going to lose consistency. Going to a smaller V opening is going to increase the spring back. It's going to create worse tooling marks. It's going to increase the tonnage. And the tooling geometry really matters. A larger shoulder radius is going to slip a lot more. In a cute die, your part is likely going to slip a lot more. Another interesting way is to use rotating dies. This picture is from Wilson. This is the V series black die. You can see these semicircular rotating inserts keep constant contact against the part, and this hard surface helps to prevent the blowout. Nice thing is they also reduce marking, and you don't have another post-process to have to do after the fact, like drilling out or welding a bend line slit if you can't have a slit. Don't have a cam rotary die available? What about trying to use a sacrificial backer? Using a sacrificial backer, you can place a piece of material that is hopefully the exact same material, grade, temper, etc. And in doing this, it can help bring around short flanges or holes that might otherwise blow out. It works best on smaller features. If you have a really long feature, that's probably not going to work. And you also have to keep in mind that the material, the backer, is deforming as well as your part. So as that part deforms, and say like the small little window we have there, that's going to put pressure against the backer material. If the backer material is too soft, that part will cut right through the backer. How about holes that are not just holes, but windows or maybe interesting shapes, miters, radii? All of these are also going to blow out. So we need to find a way to deal with that. One way to deal with that is to basically remove a slit, tabbing the material in. You can also call that silhouetting. These are terms that are for feature lines that are not cut to keep the skeleton together. This will keep the support during forming because there will be material. And then after the material is formed, you can go back and cut that material out. For a window, you may need to leave a little space. It might be difficult to get in. We can also, for miters, which tend to twist the part as it's forming, we can leave extra material tabbed on so we can form it and then cut that extra material off. as I have here in this example. Sometimes adding that extra material is twofold because you're adding distance to the back gauge. If we had cut that miter, you'd only be gauging off a small section, about 2 inches there. But by adding that extra material on, you're increasing the width. And so you've now got your back gauge further apart, and it's going to increase your accuracy. How about machine surfaces? Machine surfaces are a very interesting one because you need a blank to take up the empty space. If you were to bend this without that blank in there, the punch would never contact the machine surface and it would blow out. If you put a wrapper on the top, it's going to act as if a wrapper on the punch, changing the radius of your punch. If you put it on the bottom, it's going to act as if it were a sacrificial backer. Both of these support the material, but they support it in different ways. You have to think about how the elongation rates may differ. In the material where the entire material is together, the elongation is going to be different than the area where the material has been machined away and used a sacrificial blank. Hiding in plain sight. Deformation occurs along the material edge. Some of you may have noticed this as you're bending pieces, that the edge blows out. This is because of the Poisson effect, as they call it. Essentially, imagine a rubber band. If you were to pull a rubber band latitudinally, it's going to expand. But when you, or sorry, I should say that again. As you pull a rubber band longitudinally, it will expand. But latitudinally, in the center, it will compress. This also happens in reforming material. The blue line I've drawn here is the neutral axis. Everything to the inside of it is going to compress. Everything to the outside of that blue line is going to expand. As that compression occurs in the longitudinal direction, it is going to create expansion in the latitudinal direction, as you can see here. I've tried to draw that blue line there to also indicate the neutral axis, but it did take over a lot of the space, so I have another picture right there. And you can see the side of the material blown out on the interior of the bend. On the exterior, it has compressed inward. This can cause issues if you're using a side gauge, because that blown out area is now going to affect what you're touching. And an easy way to avoid that is to put a shim on the side gauge. The side gauges from Wilson Tool, you should check them out. They're some of the absolute best side gauges I've ever used. Moving on, let's go to bending large radiuses. If you need to bend large radiuses, like profound radiuses that are 10 or 20 times the thickness of the material, or you need to bend transitions, such as for the HVAC industries, food and beverage industries, you're probably not going to want to buy a very specialized tool unless you make that part all the time. And why? Because if you make that part all the time, you can afford the tool. But if you're only making one or two, such as in the situation of a high mix, low volume shop, you're not going to want the tool to sit on the shelf. Step bending is going to require tribal knowledge from your shop. You're going to need a skilled operator, and you're going to need the right product mix. Sometimes you can use multiple of these techniques in concert. Here we have a bend line slit in the corner. This slit helps allow the material to come around. Here we're doing a series of small bends. These small bends are in close proximity to each other, but they're not going to make up a true radius. Instead, you're going to have a series of flat segments, which will be slightly visible on the inside, though they can be polished out. And you really won't see much on the outside, but you might see a little bit of a flattening step. The distance between these bends is called radius pitch. And the smoothness of the bends is going to be dependent on the number of bends and angles you have. The more bends you have, the lighter the angles, the smoother it's going to be. The opposite will make it very choppy. Sometimes you'll want to do a choppy bend because it's just about getting it done, getting it through. but sometimes it needs to be very smooth. Often you need a smooth flow of product to prevent buildup, such as in the food and beverage industry. Here we have some calculations. The calculations are going to be basically determined by the person running the job. You can do two different calculations here. The arc length divided by the radius pitch will give you the number of bends in your step bend. This is a great way to bridge the die gap if you want to ensure that your material crosses the die and does not fall inside. Another way is to ensure that the bends are very soft and have a smooth finish. You can take the total number of degrees and divide it by the degrees per bend, and that will give you the number of bends. So for example, if you'd like a smooth finish on 12 gauge stainless steel, you might want to go with 2 degrees per bend, or you might want a radius pitch of 1/8. Workaround number 1 would be allowing the workpiece to fall within the die opening to avoid choppiness. It can be very tricky to let the part actually fall within the die opening. This is because the penetration is going to be a moving target. As you bend the first bend, it will come up normally. But as you put the second bend on, the first bend will be inside the die opening. This makes it very difficult. You'll have to go down further, and it will continue on all successive bends until all of the bends bridge across the die, at which point you will be hitting too hard and you will have to lighten back up. This can be very difficult to do. Another workaround is using a strip of urethane to take up the volume in the die. Often, this strip can help create support and have a very, very small radius pitch because there's constant contact. It's also very helpful to draw a black line straight across the urethane. Helps you line everything up. Here we have to look at what's occurring when we're actually checking our segments. In blue, I've drawn a radius for a radius gauge that we're using to check our bends. And on the left, you can see that the radius gauge will not go all the way down to where the part is. It's going to be held back away and it's going to look incorrect. So one of the things you can do to draw the material into that radius gauge is you can cheat the angles. If you cheat the starting and ending point angles by half a degree, it will help draw that in, but it may parabolize the shape of the radius. That's the center. On the right, I have instead chosen to cheat the starting and ending points instead, keeping the angles the same, but cheating the radius pitch by half. This helps to move the interference point to where the start and end actually need to be. Step bends magnify errors. If you have a half a degree error on your bend, and you put 10 bends on the part, you now have a 5-degree error. If you're putting 45 bends on a part, that error is going to be tremendous. You need to take the time before doing a step bend to ensure that the part is going to be good, straight, accurate. You're going to prevent canoeing, and you need to potentially get some test material. A test material from the exact piece that you cut, usually scrap or drop that comes off the sheet, is usually best because sheet to sheet variation could be an issue, especially with the stacking errors. This is all about finding balance though. Sometimes a process may be better or worse depending on the shape of and cost of the part. Adding a process takes time. If you have one part to do, any process is probably fine. If you're doing 100 parts, you might not want to spend the time drilling them all out. Designers and manufacturers need to work together to salvage parts that would otherwise be unusable, and hopefully work on it before it gets to the shop floor.
Fantastic.
Thank you.
Fantastic, Justin. Thank you so much. That was amazing.
Thanks.
And How many of those workarounds and creative approaches did you devise the hard way versus the easy way?
Well, every single one, I'll say. I definitely run into every one of those issues, and they're difficult, and it took me a long time to figure a lot of them out. I certainly didn't come up with them. I found them through trial and error and other people, other mentors teaching me how to do that, and excellent tools from Wilson Tool that have obviously helped me along the way.
Awesome. Excellent, excellent creative approaches. Well, we have a lot of questions. Some of them might be for Paul. I missed them before, but Brad, why don't you go ahead with those questions?
Alrighty. Yeah, and thanks. Keep them coming, everybody. Yeah, specifically for Justin, with the press controls today, can you program in the high radius and the number of steps when you're doing the large radius step bending?
Yes, you can. One of the issues is, again, if the bends actually fall within the die width, the calculations will be incorrect because you're going to need to add a bunch of corrections. But if you're staying outside of the die width, those actually work pretty well for the most part.
Okay. And yeah, back to there's a few questions still on K factor. How much does a profile vary if you adjust the K factor from 0.33 to 0.67? Is there a formula for how much the K factor would vary?
I don't have the formula memorized, but if you search DIN 6935, you'll have a lot of data on K factor and bend allowance.
Okay. Okay, good. Thank you. And let's see, this is a little bit longer question. So the CAD software uses a single K factor and bend radius to model a part. But in reality, the person asking the question says, in reality, different angles have different bend allowances, and the K factor varies, even when the material and the tools remain constant. So he says we can't use the K factor and bend radius for 90 degrees on other angles since they're different. So what's the solution here? What's your take on that particular scenario?
Yeah, that's one of the problems with the K factor formula. The formula to solve the K factor does not include the bend angle. It's assuming the bend angle is a constant. So I think we mentioned earlier, the K factor that you use will be an estimate, a guess, an approximation, and then you have to do some trial and error bending. And hopefully you have a way of recording that trial and error bending so you don't have to reinvent the wheel every time you bend that part.
Good, thanks. Okay. Lou, did you have a question for Justin? I think you guys talked about something.
Yeah, actually, I had a couple. Paul, early on in your presentation, there was you had an image of a hole feature within the V opening, and I was going to ask, what do you do about that? But during the group chat right after, the consensus was, well, you don't do anything, you just don't design it that way. And then Justin, you offered workarounds for a number of issues, and all of that led me to think, between the three of you on the panel, are there best practices, or is there methods or ideas to bring design onto the shop floor, or work with designers, or have them, have these problems weeded out before you're in this type of production? I mean, what have you seen out there, or do you have any ideas for people to kind of, lessen those chances?
I can tell you from a tooling standpoint, it is good for the shop and the business to know what are the tooling capabilities. So if engineering, design, and everybody knows what the tooling capabilities are, what is the smallest flange that the tools can handle, what is the inside radius that they are going to make or create, that will go a long way, because as they are designing and creating, If they do it along the side or around the capabilities, that will minimize a lot of the back and forth that usually goes on between operations and engineering. It'll reduce it a great deal. Which you guys have experience of that.
Yeah, communication between the designers and the operators is instrumental in resolving the problem. I was at one shop once where the operator said the designers hate us.
That's very common.
And I said, what are you talking about? He said, look at this part. And he's showing it to me. He should be showing it to the designer. And ideally, if you can use your press brake operators to help educate the designers, this would resolve a lot of problems, because often on the shop floor, the operators just assume they hate me. And this is my punishment for today.
It's true, and to that point, Paul, I think if engineering or the team starts including the operators, that go a long way. If they start taking into consideration what the hoops that they have to go through, it'll be an eye opener for ownership, management, to perhaps go about it a different way or change completely the way that they do it.
So Justin, going back to some of the things that you were discussing, I really liked one in particular where you had probably 5 different alternatives for the approaches. If this one doesn't work, try this one, and if that one doesn't work, try this one. And if everything else fails, this is your go-to. Tell me a little bit about how you came about to realize that, there has to be more than one approach in some cases.
Well, sometimes the one approach just doesn't work. I know one of the first approaches I had learned was putting a backer behind the material to help bring it around. But it really doesn't help that much. It helps a little bit, it helps in certain circumstances, but often if there's a hole right there, like almost in the middle of the bend line, the backer's not gonna work. You need to do something else. And then it was a search for what can we do that's different but similar that you can still do out on the shop floor. And that's when it's maybe try a smaller bottom, maybe try getting a roller cam tool that will help bring that around, because that's something that can be done. Well, I mean, you have to order the tool, but it's something that can be done on the shop floor. It doesn't need to go back to engineering to have them rework it. But then you start to wonder, well, what can we do ahead of time before it comes out on the shop floor? How can we modify the blank in order to make sure that everything goes smoothly? And it really does come down to the engineers coming out and talking to you and saying, hey, do you think this is a problem? And talking to the engineer ahead of time and saying, hey, often we do parts that have, a hole that's close or whatever. Maybe on this specific material, if it looks this way, just come out and ask. And then we can talk about it together and figure out a solution.
Well, I really liked the one solution that involved, just creating a pilot hole, a small pilot hole that you then had to go back and drill later. And yes, you're right, that does add extra time and another process. But, I imagine that there are some designs that just really have to be done a certain way. In particular, if the customer says, adamantly, nope, and the hole has to go here, something has to fit in there, a fastener. It's part of the whole design. It's great that you have some ways to achieve that if it has to be done that way.
Often you're wondering, well, what is the hole for? Because that might be important. If it's just a through hole for a bolt, maybe a little deformation is okay and it doesn't really matter. But if it's a hole for a pin that's got to go on, a guiding pin, it's got to be really good.
And to that point, you should include, I would suggest going as far back as the quotation or the quoting process. Have those guys that are responsible for selling or quoting, asking all those questions. What is the hole for?
Right.
The tolerance is there. How, do we need to hold them? Would a little bit of deformation be okay? And that will affect, as you guys know, the pricing of the part, to how long. Do we need to take it secondary steps? But just having the communication, having everybody involved.
Yeah,
It will
because
put down
you have to
great
add a
deal.
secondary step later on. That's cost that you did not account for.
Right. So, yeah, that could affect the pricing, and that additional pricing may change the customer's mind too about the necessity to have that hole, and that's fine.
I have seen some drawings where the designer put on the drawing whether deformation is acceptable or not on certain geometry. So sometimes, like you say, it's a clearance hole and deformation is acceptable, but on a typical drawing, you have no information to work with.
That's a great idea, really great idea. And in a previous MetalForming live session, we talked a lot about various materials. And of course, the various materials are going to change the necessity of certain features. What types of things have you run into related to changing a design or changing an approach based on the material? They come to mind.
Well, from a tooling standpoint, it's going to be how much spring back does that part have, or that the material has. That may or may not require a new tool. It may or may not require a different tip radius. Also, the thickness of the material, or how consistent that material is coming in on the back door. That all those things have, also the quality of the material coming in. You would not think so, but they do have a great impact on the finished part. And sometimes from a tooling standpoint, it may require you to get either a different angle tool or a specialty tool, like Justin was saying.
Interesting. And Justin, you mentioned that, even the sacrificial backer, you want your sacrificial backer to be the same, from the same cut of material, just because apparently it makes that much difference.
Be very different, just like we have a tolerance on the part. Maybe your tolerance is 10 or 15 thou. You make 50 parts, they might not all be exactly the same. It's the same thing with the material that comes from the supplier. I mean, they have a tolerance not only in the thickness, but also in the edge. The edge is allowed to be a different thickness than, say, the center of the sheet. And as they're coiling it, and they roll it off the coil, there could be deformation in that coil. And they might run it through rollers in order to stretch the material out and try to change it so that it's flatter and perfect. But you still may even have some residual stress in it. And then when you cut the material away in the blanking process, your parts may twist and
The memory comes back.
Yes.
It happens with 14 gauge stainless steel usually. You bend it, it's straight, and then you bend it and it comes back. So make sure that if you're buying material that is stress relieved, and that'll help with that.
Yes. You had a comment.
Yeah, I've also seen kind of a trend in the industry, especially for transportation, where everybody wants to make the vehicles lighter for less energy consumption. So consequently, they're using higher strength materials. So quite often, higher strength materials require more robust tooling solutions.
Yes, it takes the bending to a whole nother ballgame. Yes, absolutely.
Interesting. So Brad, I think you had one more question up there, or more. Or maybe not. Maybe we lost him. Well, with that.
I'm sorry, I'm here. There
Sorry,
are
Greg.
actually several questions. Gosh, where do I go? Here's a good one. Can you provide references or standards for press brake forming that include some guidelines for bend radii, such as those for knife edge forming and the relationship between material thickness and bend radius? This viewer in particular is looking for baseline standards and useful leverage point for those parameters.
1.25 times the metal thickness
Okay.
for the bend radius.
Okay.
It's the sweet spot.
Okay. Any references come to mind that we can point people towards for some of those other guidelines, knife edge forming, for example?
Well, if somebody wants to use a guideline to know what the minimum flange that the tool is going to handle the die or the inside radius, and if they are air bending, they can use an air bending forechart, and there they can reference the material thickness. Then based on the material thickness and the size of the bead, we'll give them, or we'll make reference to the tonnage that per foot that is going to take. What is the smallest flange that the die will handle, and also what inside radius is going to create. Always keep in mind that when using an air bending foreshart, that is based on mild steel and is to an 88-degree bend end. And it's bring back to the 90. But if you're using stainless steel or aluminum, there are formulas that you have to follow that they're usually included in that.
And if I could interject here?
Yes, please.
One of the things you also could do is contact the material supplier. Often the material supplier will give you a minimum bend radius that you need to follow where the material might crack. Often that's on aluminum, especially higher temper aluminums like 6061 T6. If you use a radius that's too small, it's going to bust wide open right on the backside, and it will be no good, and you won't have anything you can do about it at that point. It's too late. But they'll give you guidelines for it to tell you, and those guidelines are generally based on the grade, the temper, and also the thickness of the material itself.
Excellent idea. And that's going the extra mile, and I'm pretty sure you have done that, Justin, so it's really great. So we're moving on to our third presenter, Hector Velasquez, sales engineer, Wilson Tool International fame. Regularly instructs on how to optimize and select the correct press brake tooling. He'll let you in on ways to expedite your process and how to allow the tooling to last longer and to perform better. So I'd like to turn this over. I'm pleased to present Hector Velasquez.
Well, thank you, Kate. As a matter of fact, when working with customers, those are the two questions that I get asked the most. What do I need to take into consideration when choosing the right tools? And in addition to that, once I make the investment, how can I make the tools last longer? So today we will talk about precision tooling versus conventional, when is applicable to each. Surface treatments, what do they do? You know, what are they good for? And then once you have the tools, right, what do you do to take care of them, right? One of the things that I always recommend to customers is that whatever they put in place, to make sure that it's simple, because otherwise it's going to be taken as something cumbersome or additional work, and the employees may not follow through with it, right? So let's start with how to optimize the tooling that you have. One of the things that we always advise is that you should use the tools for the correct bending application. I understand that there are going to be instances in which you may need to cheat a little bit, but you don't want that to be the norm, because your tools are going to wear out faster. And the worst case scenario, if you're using too thick of material in a small P, you can break it. And based on the age of that tool, the material may kick out, or pieces of that tool may, shoot out and injure the operator. So always make sure that the right tools are used for that bending application. Another big one, if you guys are looking at the picture on the presentation, is cleaning the tools before you store them, or cleaning the tools before you start using them. Especially if you are bending aluminum or anything that has been coated, galvanized, galvanneal, galvanule, anything that whenever you bend is going to create what we call galling or buildup. As you guys know, when bending material, we can do something that is called shimming, right? It's placing little pieces of paper underneath the die that changes the angle of your bands. So imagine if you have too much buildup, that can essentially also change your bend angles. So one of the things that you can do to reduce material loss, also reduce downtime, is to ensure that whenever the operators, before or after, they take a little brush and they clean the die. I recommend doing this directly onto a trash can and not onto the bed of the machine, because you have too many holes that these little pieces of metal can find their way in. And if you have a hydraulic die clamp, you don't want to damage the bladder, right? Also, the top picture, if you've made a big investment, there's no cheap tool, right? There's not such thing. You're making an investment. It is very important for the longevity of that tool that the operator places those tools in the right spot. As you can see there, there is a very nice cabinet, but somehow the operator decided to put them right on top of each other. You have to realize that these tools at times are very hard. And if the tip radiuses start hitting each other, you may damage those. In the example that we have here on the picture, if someone hits the cabinet where a forklift is bends too close, take a turn too close and bends, then you have thousands of dollars sitting there that may hit the floor, and that's, it can get expensive pretty quick. Also, another way to optimize or to ensure that your tools last a long time is matching your tool angles, right? If you're using 88-degree tools, make sure that the punch and the die are 88 degrees. If you're using 75 degrees, that you are following. What happens a lot of times when operators are trying to find additional clearance, or they trying to do something that has Paul put it, the engineering team didn't like them that much that day, right? And they're having to start coming up with ideas. A lot of times you see the operator using different angles. If the smaller angle is on top, no issues. But if you invert it and you put that larger angle on top, it could break the die. And that's something that unfortunately happens. You have a lot of things going on and you step on that pedal a little bit too long, or you do the math wrong, and now you need to buy a new die. I like the business, just not that way, right? Another big one, and this is applicable for all tools. It doesn't matter if it is for precision tooling or conventional tooling. If you are bending smaller parts, make sure that you're moving to the right and to the left of the die. What happens is a lot of times we just want to hit our numbers, right? We have to bend 1,000 or 200, and the operator just bends in the same area over and over and over. It's not going to happen tomorrow. It's not going to happen next year, but over time, you're going to start wearing that area at a greater speed than the rest of the die. So what I recommend is you move to the right and to the left, and that helps with the longevity of that tool. So another question that we get asked a lot is, when do we choose precision versus conventional tooling? And usually what I tell customers is your tolerances, how do you have to be right spot on, right? Or is this something that you have a long run, or is it a short run, right? If you find yourself having to hold tolerances that are very tight, and you have to do thousands of parts that they have to be just right, or even if those parts are going to be assembled with other parts and go inside, bigger boxes, precision is going to be your best friend, simply because you can hold that precision, and you're going to have consistent parts from one to another. Another benefit of precision tooling is it happens. You're going to break a tool. If in the case, let's say it happened, right? The precision is going to guarantee that you can buy another one and it's going to match. You don't have to worry about that area. However, if you have conventional tooling, it is impossible to match it because it's made with a planer. So if you break a conventional tool, guess what? You're having to buy the entire length again. But there are some instances in which conventional tooling is applicable. On the heavy bending side of things, or if you have to do just a few. I don't have the tooling, Hector, but you have to do a few. And then you just have to say, okay, the conventional tooling, it's going to work. Along with the precision tooling, not only is going to give you the longer life that being able to hold tolerances, it also is going to help with the longevity, because usually they will have some sort of surface treatment. And you might be asking yourself, why is this important? If you live close to the water, if you live in a place that snows a lot, there's high humidity, condensation is inside the building, it can build on the metal of the tools, and they can start creating that brown rust that if you don't remove it, it can be detrimental to the tool. So having some sort of surface treatment is not only going to help in avoiding the corrosion, but it also can help with the lubricity needed. Sometimes whenever you are either bending like galvanule, one of those materials, the coating tends to transfer onto the punch tip or to the shoulders of the die. The lubricity from something called nitrex, right, is what we put on our tools, not only make them harder, but they also help minimize the galling. In addition to that, Justin, I don't know if you've experienced this, if the tool is just raw metal exposed and you have to hit the part too hard, sometimes it can get stuck on the punch and you have to hit them to get them out. Having some sort of barrier there will help minimize or avoid that from happening. A big one, it has to do with cost related, right? Is this an investment regardless if you're buying precision tooling or conventional tooling, right? Having a surface treatment on the tools is going to help with the longevity of those tools. I have customers that have 15, 20-year-old tools that they still using because not only they took good care of them, but because of some of the surface treatments that the tools have. All right, so the one question that we always get asked, not only from new customers, but also from existing customers, what are things that I need to take into consideration when choosing the right tools? And the first thing that you need to look at is the machine capabilities. Many times customers just, I found this great deal online, this great machine. And then whenever you start having a conversation about the geometry of the part and what tools are required, you find out that, hey, your machine doesn't have what it takes for that part. So the most important thing always is going to be tonnage. What is the tonnage required for the parts that you're trying to bend, right? In addition to that, depending on the geometry of the part, how much open height do you need? How much stroke? Is it going to be required for you to get down to the bottom of the V? Also, with that, the depth of the machine itself. How long can that part be, or how deep can I go into the brake to be able to make the part? And also, of course, how the length of that bed. So always keep in mind and be mindful of the press brake capabilities, because not always, sometimes you can go to a bigger die to decrease the tonnage, but it may not agree with the geometry that is being called on the print, right? Anytime you go larger on the V opening, your inside radius is going to get larger as well. So it may or may not work. The second thing to take into consideration is going to be the profile of the actual tool. So there are many questions. Number one, what is the bending style? Are you coining? Do you have a mechanical brake? Are you bottom bending? Are you air bending? So that's one aspect that you have to take into consideration. In addition to that, what are the material type and thicknesses that you are bending? Or what are the material type and thicknesses of the part that you need this tooling for? As you know, aluminum is a lot softer than stainless steel, so a different tip radius on that punch may be required to match the material thickness to avoid any cracking. As for if you're just bending stainless steel, it might be a little bit more robust or resilient, that you might be able to get away with what you have. In the case of air bending, always keep in mind that die is going to be the driving factor, right? He's going to pretty much determine what is the tonnage, right? Also, what's the smallest flange that you will be able to bend, and what inside radius you are going to end up with. Now, aside from that, there are many profiles. And if you have, perhaps if your material is very thick, you may need something like a block punch. All you need is just a hammer to drive down the material. But if you have a part like as we see on the screen there, then not only has it's a U or a channel, but it has a return flange going back in the front and in the back. So additional clearance is needed on the part and the height of that punch. So this is something that we can help you with in identify. But again, before you take on a job, just make sure that you take the machine into consideration, as well as what are your tooling capabilities at the time. Also, what about the part? This is the most important thing. Do you have parts as what we can see here on the screen? It looks very simple, but whenever you look at the form one, you can see all the different flanges going in different directions. You have holes that are close to bend lines, and this happens to be a high running part. So precision tooling was required for this, not only to ensure that you can be consistent, but also tooling that was going to avoid those holes close to the bend lines from deforming, and having sectionalized tools that will help the operator, or allow the operator to have different stations that they can move to the right and to the left without having to change or stop to change the tools. So aside from standard tools, here at Wilson Tool, we can also help you with improving your productivity from the tooling standpoint. This could be that at times, let's say, taking the first bullet, the offset. Earlier we were talking about joggles, right? So if you have to make 1,000 of them a week, you may not want to hit that part twice. You may want a tool that you can just put it in, hit it once, and move on. In addition to that, if you have a tool or a part that usually needs a punch, right, a punch press, and you don't have it, most shops today, they are pretty much going to lasers and press brakes, right? That's the norm. We can help you with tools to make forms that are usually done on a punch press. Also, we have what is called one-hit tools. If you have a box or something that has several bends, we can make a tool or design a tool that you put the part once, one hit, and you have a complete part. Again, this is just to ensure that productivity stay high, and we help you reduce the downtime. Now, one thing that we recommend a lot when applicable is the use of staged bending. Earlier, Justin was talking about step bending or bump bending. There's also staged bending. What is the difference of them? Well, stage bending allows you to have multiple setups at one time. And it could be an offset, 30-degree tool, a set of flattening tools. It could be many tools. And you can see this from two aspects. If you have a shop in which there's a lot of tool changes, right? 3 to 5 per hour. And you have very short runs, 2 of these, 5 of those, right? So you can go ahead and have the operator can go ahead and set up all the tools at once. And instead of having to stop in between jobs, they can just go ahead and do the first job, move on to the second one, and so on, keeping productivity high. In addition to that, if you have a part that is very complicated that requires different tools to be used, and usually you have to, let's say it's 100 of them, and you do the first 100 bends and you're planning to stopping, getting the second setup and going to the second one and so on. If you have the real estate on the press brake, you can have all your setup already there, and you can go first bend, second bend, third bend, and be done and move on with that. If you asking yourself, well, my parts are 10 feet long, stage bending is not for you, right? This is just for smaller ones, shorter, smaller parts. So let's move on to tooling maintenance. When it comes to tooling maintenance, a lot of times I'm asked, how often should I do this? And there's not a like a specific answer for that question. This is all going to be based on usage. I would say every time you use your tools, you should do some sort of maintenance. Either it's going to be for you to remove some galling, and we have some videos at wilsontool.com that shows you how to remove that. It could be removing the little metal shavings from the V, right? Also, another big one when it comes to maintenance is going to be if you live in an area that is either close to the water, we have condensation inside the building, is putting some sort of oil on your tools that will create a barrier that will keep the brown rust from forming up. And also a big one is going to be storing your tools in the proper place. If you have tools that have some sort of tang, safety tank on the punches, such as American tooling and what we call WT tooling, we recommend that you take a look at the safety tank itself to make sure that it's not damaged or worn, and that the screw, that button that goes in and out, that's also a screw. Make sure that it's nice and tight, right? And that brings us to the end.
Excellent, really excellent. You know, we were talking about this earlier, and that, you know, on every auto mechanic will tell you that the right tooling will save a lot of time. And I really liked your discussion of the specialized tooling, and particularly the one-hit tooling and so forth. So we have a lot of audience questions. So I'm going to turn this back over to Brad. Go ahead with your questions, Brad.
Terrific. And thanks for everybody for hanging in there and for asking all these great questions. We'll get to as many as we can. I'm going to go all the way back to Paul's presentation, and you kind of glanced over this whole question of die marking, and I know everybody online, everybody that's got a press brake is dealing with die marks, especially on aluminum and stainless. Can you guys offer a few tips on how to deal with die marks, how to minimize or even avoid them, especially in the question specifically talks about aluminum and stainless?
Yes, so the most inexpensive way to take care of that is going to be by utilizing urethane or a fabric drape that will keep the marking from taking place. If that is not enough, then you could buy a die with a bigger or larger shoulder radius that will also help eliminate the die markings.
Okay, any other input on that, or that?
Also, you can also reduce the friction by putting on tend to use like WD-40 or CRC fluid. I know often with like aluminum, because aluminum tends to stick, I'll spray it down, I'll wipe it off, so there will be a real thin lubricity layer right there. Put the bend on, maybe do 5 or 6 bends, then you might have to reapply it, and it also gets on the parts, so it's another process, but it can help in a pinch if you don't have the brake film on hand.
Depending on the part also, they are urethane dies. Be careful, tread lightly, use them, test them before you go buy a whole lot of it, because depending on, sometimes the angles are not held. So for smaller parts, I recommend it for smaller parts, not long parts.
You can also bend with the backing. It's expensive because it's disposable. You throw the backing away. But if the flanges have to be absolutely pure, like in the aerospace industry, often a backing is used.
Very interesting. All right, back to you, Brad. Another question thrown at us.
Yeah, this one could open up lots of discussion perhaps. It's the very first question that we got, but so you guys, I think, all addressed another maybe the issue of the day, right? Which is how do we improve our processing time? How do we get more parts out of the press brake per hour? I'm sure Justin deals with this every day. And you guys offered some tips along those lines, but if you want to go back and revisit maybe some of what you thought brought up already, or if there's some new discussion that somebody wants to tip off here about the best way to just improve throughput. Obviously, we want to improve throughput without jeopardizing quality, but I think that's the key.
Yeah, so of course, just spoke a little bit about stage bending. So implementing a tooling style that will allow you to have multiple setups will help. In addition to that, if they can go back to how the jobs are coming through, and if you have parts that will require the same tools, perhaps you want to have them together. And then as you put other jobs that will require other tools towards the back, grouping them together, that may help in minimizing the downtime.
I know, specifically for me, I know my job helps me out a lot with it. We'll have a lot of jobs that are all due. They'll give me all the jobs and say, hey, I might need this job right now. It might be really hot. You need to do this one first, but then do whatever else you can that matches that same setup or similar setup, or even maybe it's a similar material. A lot of times those can really help. Or if you're just doing long parts, maybe you want to do all the long parts and then go work your way down to all the small parts slowly or something like that. I know another thing that really helps though is processes before the break. Like if you're, say, punching a part and then you deburr the part and then you just throw them all on a skid and you hand it to the brake guy, that may not be as good as when you're done with it, you lay the part down in a specific fashion for how it's going to go into the brake. You lay all the parts the exact same way so that when the brake guy gets the parts, he can pick them up, put them in the machine, bend them, put them to the side. If he's going there and sitting through and picking them out and doing this, that's a lot of wasted time that you might potentially be able to avoid in the process before.
Wow, great, very interesting. Great, very specific suggestions and really good ones. And Paul has some.
I would say one of the big solutions is to address all the issues offline. There's a number of offline softwares where you can see if there's going to be blowout. You can address the blank size. You can assign the tooling and you can do the simulation. So you have a huge savings by coming to the press brake with a finished product. The other big solution would be to group parts according to the tooling. Your biggest part of your setup time on the shop floor is normally the tooling. So if you have jobs that can be grouped according to the tools, you can save a tremendous amount of tool changing time by grouping the jobs for the tools that are in the machine. Yeah. But I've seen a lot of operators when they have the tools set up, they feel like their machine is tuned in really well and they call it a hot setup. So if you go from job to job with a hot setup, there's practically no adjustment time in between.
Oh, that's cool.
Yeah, also you
Sort of
can
like a
utilize.
lucky streak at the casino.
Like a lucky streak at the casino, when the machine is kicking out good parts, bring me more before I have to strip the tools out.
That's interesting. So Justin, you're shaking your head. You
Save a lot, yeah, like especially on a longer job. Sometimes we'll do a really big, long step bend. You take a lot of time to really get all of the wedges even, get all of the deflection so that it's all perfect and your angles are good. You don't want to tear that out and do something real small and then put it back in to do another large step bend. If you already got something going good, even if it's not a step bend, maybe you've just got long channel parts, but it's still a couple bends together. Your machine's already set up and good to go. You don't have to reset up anything. You're just changing the size.
Well, I'm just gonna break here just for a moment. It looks like we reached 3:30 already. We're going to continue talking a little bit longer, but for those of you who have to leave, go ahead and send your questions if your questions have not been answered. Send your questions to Brad Kuvin. That's BKUVIN@pma.org, and we will try to get those questions answered for you. So we're going to continue a little bit longer. Brad, did you have any more questions that you want to throw at our panelists?
Actually, Kate, I do have one.
Oh, yes,
I-
yes,
uh,
this is an important one for Hector, right?
Actually, it's for anyone who wants to answer it, but yeah, with Hector and talking about ways to improve throughput and while maintaining quality, the time may come where you have to invest monetarily to do that. Whether it's in some kind of automation or tools or whatever. And Hector, maybe we could start with you, like and this is important if the shop floor needs or production needs to justify, a purchase to management or whoever holds the purse strings. When you provide a tooling solution, what's your answer when it comes back to you? Well, that's too expensive.
Very good question, and thank you for that one, because that's one question that I have to address weekly. And it is up to us that do this at Wilson Tool to sit down with the person making the decision to show them or walk them through how much is costing them not to have the tool. Because there's a cost already. Either you're not able to get that job, or it's making you, your guys are having to go through a lot of hoops to make that happen. So it'll take for those, the decision makers and us, to sit down and just walk them through what is your shop rate, what is the hourly rate, how much material loss, how much downtime, and then showing how much is currently costing them. So I usually turn the question around and I said, it's not how expensive or how much it is how much it's costing you for not having it. So that's usually what I do.
It sounds like a good strategy for those of us who might be wanting to make an appeal to our spouses to purchase something. Let's say an expensive car. How much is it costing us not to have that Maserati, honey? So anyways, Justin, did you have a thought about that?
I thought to add on to what Hector said, one of the costs that you really can't judge, it's hard to judge, is the amount of stress that it puts on the person that's doing the job too.
That's huge.
Because that person maybe doesn't want to come into work. They don't want to be there. They don't want to struggle, And not only are you saving the time and the money for the company, but you're saving that person that aggravation. They want to come into work because they got a tool to solve the problem.
That's a great angle, and employee retention is something that I will give you credit the first time, then I'm gonna use it as my own.
I would say that it really is an excellent point. And, obviously skilled worker shortage is a huge issue right now, a huge problem. And, I really appreciate that coming from your perspective. How much stress are you putting on that operator who has to accomplish this, impossible part with the tools they have, with the circumstances they are? And, everyone wants to feel successful in their jobs. And, you can encounter a certain number of obstacles and, maybe feel good about surmounting those obstacles. But then what does that do if you have to deal with that every single day?
And Kate, now that's a great point. To your point, Kate, the skill level coming in is not the same as before. Or finding a good employee is found to be more challenging than before. So having a tool that will make things easier for the operator, and at the same time, you're not having to run the risk of them putting the wrong information in the machine or having to do the math themselves, it'll go a long way.
Or the tool can increase safety too. I know we were talking about that earlier. Sometimes a part may require an operator to get close to the working area and all that. And if you can get a tool that can keep your operator's hands away and can allow that part to not only be made faster and all that, but you're also increasing the safety of the operator.
That's a great point. Yes, absolutely.
And Hector's going to use that also, and he'll acknowledge you once or twice, and then
second time I use it as my own.
So we are running a little long, so we could talk about this all day, all night. We probably did last night. It's fun, but we'll be wrapping up pretty soon. I just want to ask each of you if, before we wrap up, and close for good. If you can just comment on something, from your career and experience, the most successful part you made, or the most enlightening thing you learned or you teach people, and of course, the most special tool you have in your toolbox, Hector. So let's start with you, Paul, if you would.
Yeah, it's what you learn after you know it all. That counts.
Ah, wow. Somebody writing this down. Write this down. And I'm gonna use that. I might acknowledge you once, and then after that, it'll be my own. Wow, so profound. How about you, Justin?
Sorry, I got distracted there.
Oh, yeah,
Can you repeat the question?
I know, I was just, what would you say, like, some 52-fold part that you made that you were like,
I got one that was a really good one. We were making, it's basically like a shaker tray for like a product to flow down. And this tray has 24 bends. And you see the 2 bends on the very end of it that kick it up are 90s with the straight tool. The rest of them are all a radius bend. And you really have to be very accurate, because after you've done 5 or 6 bends, you're moving just a little bit and it looks very close. And then you do another 5 or 6 bends and it still looks pretty close. And then you do those last couple bends and all of a sudden you're very far off. It took me a little while to get good at this one. And it's mirror finished as well. So it's very, you can't mess up, it's very expensive. But now that I've got a process down for that, every time we do that part, just trying to get it done as fast as possible, but also right. And every time it comes out absolutely beautiful. I feel a great sense of accomplishment just getting it done.
very cool, very cool. And Hector, what was your greatest save with tooling that you provided to a customer?
The greatest one. Well, there are quite a few. There's not one particular one that comes up because I've been fortunate enough to provide a lot of solutions to a lot of customers. It does bring me good satisfaction when I'm walking down anywhere and be like, oh, I know who makes that. And our tool was part of it, right? But I think it has to, the biggest one is whenever a owner comes to you and say, thank you. Not only you save the job, you help the business, so for them to continue on. And that's what brings me the satisfaction to do what I do. Just go in with a smile and truly find out what is keeping you up at night. What are the things that are giving you headaches, as you're driving home, things that you're thinking about, and then providing the solutions for those.
Very cool. Well, we're going to continue chatting, but we'll let you go. But thank you all for joining us. I hope that you learned something. I'm pretty sure you probably learned a lot. I want to thank our fabulous panelists, Paul, Justin, and Hector. It was such a pleasure talking with you. I feel like I learned a lot. And thank you again for joining us for this MetalForming Live. There will keep your eyes for the next sessions of MetalForming Live. And we especially, again, want to thank our sponsors, whose generous support of this program has allowed us to bring this to you for no cost. And then I'm gonna turn it back to Brad for a final comment.
Yeah, again, just want to thank everybody for joining us, and of course our panelists, and for you, Kate, for doing such a great job of moderating. And yeah, the sponsors are on the bottom of your screen there. Our next MetalForming Live is in December. We'll be talking about servo press technology and ways to leverage that, press curves, and some of that technology. So hopefully you'll join us then. Keep your eyes open for registration information. And then we'll be back next summer with this 3-part series again. So hope everybody can join us. And again, thanks for being here today. And thanks to our panelists.
Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass, move along.